In this video, I'm going to talk about the concept map for Unit 3, which is about electric potential and charge distribution interactions. So first I'll talk about electric potential and potential energy. So this one, the symbol is indicating the electric potential energy, and electric potential energy is conservative forces, is conservative. So it is path independent, and you could just use UB minus UA to calculate the potential energy difference instead of integrating the or instead of doing integration or any more complicated stuff. So this is the full form of the potential energy, which is to integrate the force dot ds, and is also equivalent to the negative of work done. And here is the electric potential. The electric potential, same with potential energy, is conservative, path independent, so we don't really have to do the full integration form. But this is the definition of the electric potential, and that is equals to E dot ds. And if we try to relate potential energy with potential, it's basically just delta U equals to Q naught delta V, which is the same thing as saying E equals to Q, which is the same thing as saying E is equals to, or QE is equals to F, or F is equals to QE. Then we can talk about the electric potential due to point charges. So let's say we have one point charge, and we're trying to find the potential due to this point charge. So the delta V would be equals to the integration from distance A to distance B of the electric field the point charge produced dot ds. And since this is a point charge, electric field will always be parallel to the ds, the distance from the point charge to the test point. So again, it is path independent. So after some simplification, we have this form, which is much nicer. And when we take infinity as reference point, so if we take infinity as the point A, then this thing would be equal to 0. So the potential would basically equals to this form, which is way nicer. So note that the E field is also equals to the negative of the gradient of the potential, and this is very useful when we're doing calculations with the continuous charge and evaluating the equipotential map. Then we can move on to the next concept, which is talking about the potential energy with the system of charges. So what if we have 2 or 3 charges and we're trying to calculate the potential energy the system has? So again, if we're taking the infinity as the reference point, so the potential energy would basically summing up the potential energy between the two charges, between each of two charges. So let's say we have point charge A, B, and C. Potential energy would basically be UAB, electric potential energy, plus UBC, and the AC. And this is just a more complicated form, and I used a more complicated mathematic expression to indicate this concept. Then we can talk about continuous charge distribution. So when we're talking about continuous charge distribution, I have a little drawings here. So let's say I have this thing as my charge. I say this thing is charged, and I'm trying to find the potential at point P. So this is more complicated than what we've done before, because what we've explored before is about point charges, and this time we have a surface of charge, or a charged thing. So we have to do some integration. And how do we do the integration is we're saying that if we're just taking one point in the surface, we call it dq, and we're trying to find the potential due to this point. So the dv, the little potential, would be equals to this thing, which is basically this thing that we've discussed before, with here. It's the same thing. And after we set up the differential form of it, we can do the integral form of it. So after we do the integral form of it, we have this expression to find our potential. And so this is the fundamental concept as we delve further to some symmetrical charge distribution. So note that this thing is uninteresting because it is non-uniform. We don't know what this is. We don't even have a mathematical function for this thing. But if this thing becomes symmetrical, such as a rod, a ring, or a disk, or a sphere, then we can do some mathematics on it and make things nicer. So here we have a new concept, which is called the charge density. The charge density is basically saying that if I'm taking the whole charge with charge Q, and the whole thing is with distance is a wire with distance 4 centimeters, then I just have to divide the charge over the 4 centimeters to get my charge density. So we have 3 different charge density: lambda, sigma, and rho. Each represent a different dimension of the things that we're talking about. So we're just talking about a wire, and we're trying to find the charge density of a wire. We'll use lambda, and it's just basically saying that the charge density of that wire. And the area and the volume is the same thing, except we just increase one dimension of it. So we have 3 interesting things to talk about when we're talking about symmetrical charge distribution: charge rod, charge rings, and charge disk. I'll include a video to talk about charge rod, but right now I'll talk about charge ring and charge disk. So for charge ring, we have to do a lot of mathematical calculation, basically doing the same thing as this one. And some other scientists, some physicists have derived this formula, which is very useful, that we don't have to derive ourselves again. And the Z here represents that if we have a ring and we're trying to find the electric potential, and this ring is uniformly distributed with the charge, and we're trying to find this one is the Z axis, and we're trying to find the electric potential at this point, then we can just plug in this formula if we have the radius of the ring, and if we have the Z coordinate of the point that we're trying to find. The same thing with the electric field. Since it is symmetrical, it is pretty intuitive that we can find a mathematical formula instead of doing all the calculations again. And these 2 things are basically the same thing. So it's not that interesting in terms of physics. So the same thing goes with ring. We can do the same thing with disk. The only difference is when we're talking about ring, we're talking about circular wire. Then we have to use the length, and that is in terms of lambda. But then when we're talking about disk, a disk is some solid, and it's better if we use rho as the area instead of lambda, because it's not a length anymore. So the same thing with the electric potential and the electric field due to the disk. This time we're talking about, so this is the disk, and we're again talking about Z axis. So any point P here, if we have the Z coordinate and if we have the radius of the disk, then we can find the potential energy and the electric field. So that's pretty much about continuous charge distribution. Then we can move forward to the equipotential maps. In equipotential maps, we're discussing about like a contour map. In the contour map, we discuss about the steep of the slope, but in equipotential maps, we're talking about the electric potential of the thing that was put on the system of charges. So we have 4 different potential here. And let's say V4 is greater than V3 and greater than V2 greater than V1. Then electric potential always goes from high to low. Same thing with slope. We would roll from high to low if we're on a mountain. And I'm talking all these things with the assumption that I'm talking about positive charges. If I'm talking about negative charges, then it's another story. But so right now, if I'm talking about potential from high to low energy, then my electric field would point again from high to low energy, from high potential to low potential. And since we have this thing, E is equals to negative delta V, there's also one interesting thing about equipotential map is that our electric field will always be perpendicular to the potential. So to illustrate, we could think an electric field at this point would goes here. So this would be tangent to this line right here, and that is because of the differential form of equipotential. And the closer lines that we have over here, and the further line we observe over here, it means that if we have closer lines, that means over a short distance, the potential difference is larger. So we could imagine it as having a steeper slope. So the potential would drop more dramatically over a short distance. And that is about the equipotential map. And each line here is saying that this line contains the same potential for the system of charges. And that is all the concept map I have in this video. I didn't include the Fourier diagram because I don't think it is necessary for this unit. It's better if I understand the derivation of each equation than understand well, basically this unit is almost everything about derivation, so I just include the derivation here in the concept map instead of including a Fourier diagram. So that's the concept map. Thank you.